this particular presentation we are talking about here is the time and the frequency domain with the nCode software. So I am Saravana as a senior application engineer in HBM Princeton. So this webinar will have certain agenda with the introduction of whom we are as a HBM Princeton. We already know that there are certain possibilities in time domain analysis, and there are certain possibilities in frequency domain analysis. So introduction about the time and frequency domain will talk about what are the things we are doing in time domain and the frequency domain. The next we talk about how do we convert the time domain into a frequency domain. Then the fourth agenda would be on joining these two by the way of showing time as well as the frequency. So there are certain advantages to see both the domain in one single situation. So we have a certain demo which explains about what we have as a conversion of a simple frequency domain. Then it connects with joint time frequency analysis. And there are something like waterfall analysis and a frequency response function. So today webinar, we talk about a few related information about that, joining the time as well as the frequency domain. Say who we are. As a Princeton, we help the engineers to deliver the durable and reliable products by the way of avoiding cost of unexpected failures. So before any failure, is there any chance of predicting the failure with a background of mathematics? So we operate in three mode of operations. We develop software. The software brands are nCode as well as the ReliaSoft. We provide a training and education on the subject of design for reliability, design for durability, fatigue theory. All the training programs are handled in such a manner with classic examples of industrial case studies. We provide the case studies to solve in the training programs. And what is the takeaway from the problems statement and the results as well as the interpretation of the results. So the third mode of operation is the services. We provide material testing. Whenever you see in nCode software, there are SN curves. So we develop these SN curves in addition to certain standards. In case of any of the material you are developing as a customer, if you provide the material to us, so we will help you to arrive the SN curve with certain consulting mode of projects. So in addition to that, we provide the solutions for the real industrial problems from reliability as well as durability point of view. So in asset management point, we could able to deliver the problems which are pertaining to oil and gas industries, cement industries, chemical industries, and the railway industries, where the customer do have the assets and the utilization of the assets based on the reliability parameters. So from ReliaSoft, the software belongs to the reliability live testing and the system modeling and standard-based predictions. So these kind of tools are known as the quantitative approach, where we create the data by the way of real testing and analyzing the test data based on the mathematics behind that, like a live testing, like accelerated testing. From a reliability growth point of view, we do have a system level testing as a vehicle level testing or the equipment level testing. The software like FMEA, RCM, they are mostly towards the qualitative approach. So during the product development lifecycle, the engineer try to observe the probable failure mode. What is the chance of the probable failure mode based on certain industrial practices, say like FMEA standards. There are VGA standard, there are AAG standards, so many industrial standards. Based on that standard-based template, we could able to create the base level reliability on a qualitative approach. RCM is related to the asset management, the industry of process industries. They use these RCM tools. So in a whole, ReliaSoft provide the entire solution to the product development lifecycle from a reliability point of view. nCode provide the solution to the durability point of view, like a design life from a CA-based fatigue analysis, VibeSys as a test-based engineers and durability calculations, VibeSys mostly dealing with the vibration and acoustic analysis. So in addition to that, we do have a web-based platform like an Akira, which can manage the entire design life and VibeSys and VibeSys in a web-based portal, which you require a separate kind of a license like a Princia license. So maintaining the licensing and maintaining the particular versions is quite easy comparing to the desktop applications in the Akira platform. So in the today webinar, our focus will be on the VibeSys. Let us see. So as a title indicates the time domain and the frequency domain, how do we club together as a time, as linking time and the frequency domain? Okay. As a human being, as a man, we see colors, such as maybe as a man we can see very few colors like red, green, and yellow, something like that. But as a woman, the women can see many more colors. You can see you can have as a different colors which are in the red. There are some magenta red or something like that. So in a sideline notes, like something like when you visit a shop like normally it's like a blouse matching shop. You see here the blouses which are in the different colors. The lady come with a sari and the lady took the blouse which is exactly matching with the colors. So if you see here, there are so many varieties of color, but the men cannot be able to understand, but the women could be able to understand. So this is in a lighter note to see here as a colors. So why we are seeing this as the colors is the indication of the natural way of frequency analysis. Now we can see here all over the world where our life is related to colors. Just in that. So nature's frequency analysis. Say as a white light which pass onto the prism, you can see a different colors. So these colors are separated based on the wavelength, basically the frequencies. So wavelength and frequency, we have a connection between that mathematically. So the white light is the combination of colors which are added together with the different colors. So you can see in a natural way, you can see a WebGR by the way of the rainbow. So the prism decomposes the light into different colors, basically the different frequency content into that. So nature's frequency analysis is the prism. So in mathematical equivalent way of doing the frequency analysis is the Fourier transform. So when we have time signals, say why we do have a frequency domain. Say most of the time the vibration is defined as the oscillation of the motion of a rigid body or elastic body or a medium forced from a position or state of the equilibrium. So by the way, it is oscillating from the equilibrium in an amplitude as well as the time in a period, something like that. Say this implies certain periodicity and occurrence in certain intervals. So throughout our real life, there are so many natural phenomena which are following the sequences, which are following some periodic phenomena. Let's say the movement of planets, our musical rhythms, the electrical alternating currents, and sleeping patterns of the human being or sleeping patterns of the living things, and the seasons. So those are all in periodic in nature. So such a way, the periodicity of the signals is helpful in some time to arrive some meaningful results. The excitation at regular interval is easier to observe in the frequency domain, but this may not be possible in a time domain. So let's say there are differences between the time domain and frequency domain. Sometimes time domain is advantageous and sometimes our frequency domain is advantageous. Say time domain is very easy to visualize how the signal is look like. Say for example here, if you see here in the right side, the time signal, there are certain kind of squiggly lines. You can see here all the data which are squiggly in nature. So suddenly there are certain, after some point of time in the time signal, there are some squiggly lines happens, then it becomes like a small portion of this amplitude. Then it becomes, so it is like a repeated time signals with multiple blocks. Okay? So you have a multiple block over there. So it is easy to visualize in a time frame how the time signals are changing over the time frame. And of course, it describes certain transient behaviors. And it is easy to understand the phase and relationship between many channels. So the phase and its differences. It's a positive, negative, where it moves towards that. So our real life, what we deal with that is a time domain. Whatever the data we have is a time domain data. Right. So when it comes to the frequency, there are advantages. It is easy to see the pattern and the periodicity. Let's say when I convert that time domain in the picture given above into the picture given below as a frequency domain, I can see where the dominant of the frequency. Even if see here, there are 3 blocks of time domain signal, but I have only one frequency domain pattern. So the same block cycle is repeated over here as a 3 cycles, but I see only in a frequency domain with only one single pattern, because the same time signal is repeated for 3 blocks. So there is no 3 different frequency blocks like this. So it is easy to see as a patterns in a periodicity. And from a storage point of view, as a data point of view, time domain signal requires a huge amount of data storage, the memory caches. And the frequency domain may not be that much of size, and the data size, file size becomes smaller. So there are certain other statistics is possible in the frequency domain, averaging and the PSD and something like that. And there are certain harmonics you can find over here. So there are certain disadvantages in the time domain as well as the frequency domain. In the time domain, it is very tough to interpret what is that it indicates. It's because it's everything look like as squiggly lines. So, and it is very tough to see the patterns and its periodicity. The major disadvantage in the time domain is the large data file, which occupies more space over there in the hard drive. And in the frequency domain, there are certain disadvantages, like the time duration is lost. So you may not be understand that how much time it takes to capture the signal. If you see in a frequency domain, in the x-axis, it indicates only the frequency. And in the y-axis, it may be a PSD or something, G square per hertz or something like that, as amplitude in G. So you may not know the entire frequency signal produces of how much of the time frame if you don't have really the time domain signal. Yeah. If somebody gives only the PSD, it is very tough to see how much is the time of collecting this particular signal. But statistically, it is possible to reversely to generate some time signal. But by the way of first look, it is very difficult to understand. So there are certain transient behavior is lost because the signals is repeatedly done, and it shows the most of the time with the dominant frequencies. So it is very hard to get the amplitudes from the broadband of the process. So there are certain advantages and disadvantages, something like that in the time as well as the frequency domain. So now, how do we get that time domain into the frequency domain? The way of converting that time domain into frequency domain is the fast Fourier transform. And from the frequency domain, you can convert into reverse back to the time domain as an inverse Fourier transform. That's quite possible. Okay. So as a Fourier transform, so you may see here as a individual. So as I mentioned earlier, the nature's frequency analysis is a prism. So where we have the Fourier transform as a prism. So how this Fourier transform works? So way back in 1700, the theory of Fourier was developed and it was very well used like that. As a prism, if you see here as a signal which is maybe you think as a square wave, so it consists of so many signals inside into that. And so as a Fourier transform, it is split into the individual signals. By the way, seeing here, so you can see as an amplitude, the first signal, if you see as a sinusoidal wave with the amplitude of the higher side, you can see as a signal like this. Then the next signal, which may be a lesser amplitude, which goes into the this, and the third signal may be clipped together. So by the way of seeing here, there are 4 amplitudes. I can see here 4 frequency content, which is of with different amplitudes. You can see over here. At the end of the time, it's the Fourier transform, which separates that from the original time signal of individual frequency and its amplitudes. Okay. So if you see here in a pictorial format, it look like that. The summation of all the signals becomes here. That's that. The original signal can be recreated with when all the sinusoidal waves are added together. See this. Right. Okay. When we talk about the frequency domain, we might have heard about the PSD. So what is the PSD? As a power spectral density. Most of the time, the classical Fourier transform very well date back to 1700s. Okay. So this can process only the signal which can be defined by a mathematical equation. But when it comes to the real life, so it may not be following as a particular pattern which are very perfect in nature. So in early electronic engineers somewhere in 1940s, they try to see the signal of voltage at its time frame. So they wanted to calculate the amplitude versus frequency based on the measured signal, which could not be represented by an expression. What they tried to do in that time frame, their approach was to use a series of analogous filters to derive that particular plot. So how it happened, the voltage has been extracted as a time signal, and they try to implement with a low-pass filter over the range of the frequencies. And from there, they try to make it into find out the mean of that. By the way, the average of that. Since it consists of the positive as well as negative, they try to multiply again with the same signal. By the way, the squaring of the signal. This particular squaring of the signal is done, and it has become into a positive dot, because negative signal becomes a positive signal. Then it was made into a cumulative mean value of that particular signal. Then again with the certain frequency filter, it has been made into a cumulative mean square of that. Further, it has been combined together to create a particular PSD. So when we talk about the PSD derives the name from the fact that early engineers were interested to see the electrical power. Secondly, they were plotting a spectrum of frequency. By the way, electrical power, and they were trying to plot the spectrum of frequency. And thirdly, they displayed the resulting plot as a histogram. By the way, the density function. Now we can see here power, spectrum, and density. By the way, power spectral density. So power spectral density is the change of the mean square over the frequency range. So the area under the plot represents the mean squared value and not the absolute height of the histogram. If you see as a power spectral density, the area under the curve area under the plot represents the mean square value of the mean square value of the time signal and not the absolute of the histogram. So this is what a simple description about the power spectral density when we are trying to do it in the frequency domain analysis. So as a signal, there are a variety of examples like the time series as a time series and PSD. If you see here as a sine wave, which ideally represent as a signal spike centered into the sinusoidal frequency. It has only one frequency as a time history here in the first picture. You can see here the frequency. Now in the time picture as a broadband signal, you can see there are two kind of frequencies, like a frequency somewhere in the 4 hertz and a frequency somewhere in the 8 hertz. As a narrowband signal, it looked like that as a spectrum frequency ranges from maybe 2 to 3 or 2 to 4, something like that. And you can see here as a band of something like that, which the area under the PSD is exactly same as the mean of the time signals. And in the white noise, if you see here, the frequency ranges from 0 to infinite number, but with the amplitude something. Okay. You can see here different examples of the time as well as the frequency. So when we are talking about the PSD, there are certain key properties. You can see here, the root mean square is that particular equation, and the sample rate is f of s, fs, and the number of data points, a number of data points of the time signal, and the amplitude is of at. So the delta t is the time frame of our interest. Now, most of the time, what happens? The Nyquist criteria has to be C, the maximum frequency of the particular signal. Okay? So Nyquist criteria is half of the sample rate. That has to be fulfilled to see the highest frequency content in the particular signal. Okay. So as RMS is the square root of the area under the PSD. RMS value of this particular signal is the square root of area under the PSD. So this is what we will see. We see normally in the power spectral density. Okay. So when we connect with the time as well as the frequency domain in a one single portfolio, in a one single analysis, we would be seeing certain things like dividing the time signal in many buffers. So after that, calculate the PSD for each buffer. So you can see here there are different buffers like this, as a time signal is segregated into different buffers as a delta t. So, excuse me. So divide the time signal into many buffers and calculate the PSD of each of the buffers. Now let us talk about the buffers. See, when it comes to the fast Fourier transform, the time signal, by the way, the time series signal is separated into different buffers for faster calculation. Because as an entire signal, it is very, very tough to calculate. The reason is it may be because it may not be exactly of 2 power n. Because normally the entire signal may not be exactly of 2 power n as a data points. So that may contain a different data points. So to make it into the FFT algorithm in a faster way and optimize that in a computer as a digital data point of view, so we use that 2 power n as a data points. So the buffer is always with the length of the 2 power n as points of length, something like a 32, 64, 128, 256, and so on with the points. So each buffer has its own frequency spectrum. When we see about that, buffer 1 and buffer 2, buffer 3. So individual buffer is converted into a frequency spectrum as a individual PSD. So further, these PSDs are combined together to produce that as a joint frequency, time as well as frequency. Okay. Right. See, there are certain other information like buffer as well as its windowing. So when it is in the mathematical calculation, there are different kind of windows are used. So why the windows are used? Say what happened if the amplitude of the last point in the buffer, say let's say the amplitude of the last point in the buffer, let's say this is the first buffer, the amplitude of the last buffer and the amplitude of the next buffer, from if it is significantly different, then it will introduce a significant jump in the signal. That means it is like a impulse into the signal. So impulse into the signal. If you can see here in the picture, so there is a large jump between the buffer, which repeats as a result in the spectral leakage to the adjacent frequency as bits. So such a way, you may see certain kind of a signal leakage over here. So instead of a signal like 5 hertz, you may see some adjacent leakage like 6 or 7, something like that, or 5. So in between that. So to avoid that and smooth the signal, what we do here, multiply the buffer by a smooth window function. And it can avoid as a large jumps, and it limit the spectral leakage. So by the way, this can be multiplied with the window. So the windowing function will help you to provide to smoothen the function to avoid the spectral leakage. So in addition to that, this forces the start and end point to be 0 by the way of preventing the jump. So there are certain kind of disadvantage, but that can be managed over here. So by the way, unfortunately, the window function also remove some of the amplitude content of the signal. So this can be easily factored back into the PSD when we work upon in that with the windowing functions. So as a whole, many windowing functions are possible in the software by the way of panning window, camming window, hazel bezier, flat top, or triangular. There are dozens of windowing functions. Most of the time they differ in shape by the way of doing the things. But there are 3 things are common in all the windowing functions. So their start and the end time become 0 as a 0 padding, and they are try to unity at the center of the signal, and they are symmetric in nature. By the way, they are symmetric in nature from a windowing point of view. So by the way of windowing, this can chop out some of the artifacts in the time frame by the way of connecting the particular different buffers into the signals. So as a buffer overlap, so when we what kind of a overlap? So when the windowing functions, there are certain kind of other effect is possible because they attenuate large portion of the signal, so it is easy to miss some features. Say the reason behind that, because we have multiplied them with a very small number. To avoid that kind of signals, or to avoid this kind of problem, then we use the buffers to be in an overlap together. Okay. Now we can see here, so from the buffer 1, buffer 2, buffer 3, and buffer 4, buffer 5, buffer 6, buffer 7, buffer 8, buffer 9, something like that. So this is overlapped by 67% over here. Then again, this is overlapped by a 67% here. So by the way of minimizing this kind of attenuation into the large portion of the signal, so the buffers overlap is used here. Okay. Now, say many time as an engineer, we may doubt that I want a higher resolutions, and as well as I want a better time frame. Say when we see about here, when we choose this windowing and buffer, something like that. So as a better frequency resolution means larger time of buffer. Computationally, it takes a more longer time to convert this spectrum. Okay. In addition to that, if you increase the sample rate, it may not help in arriving a better frequency resolution. But what happens? It will increase that Nyquist frequency. That's it happens. So by the way, as a Heisenberg cell, either you can have a block like the block which is with a higher the breadth is more and the height is less, or it can be the breadth is reduced and height is increased. So at the end of the day, you will see a area under the curve remains same, either you increase the time frame, or you what do you call, or you compromise with your frequency resolutions. So at a time you cannot have both of them in hand. So this kind of Heisenberg cell concepts provide the idea behind that of compromising on the frequency resolution as well as the time buffers. So when it comes to the joint time frequency analysis, something like that. So let us go for certain kind of demo. Let me switch over to the software. So now I have the situation like this. Let me pull over here. So when we do it in a time domain, I'm converting that into the frequency domain. Let's see here. Say I have a frequency. Say I have a signal like this as a time signal. So I have a signal like this. Yeah. So let us see here. So in the frequency, you may see here when I'm converting that into a simple frequency analysis, like a frequency spectrum analysis. So you can see here there are certain properties like a power, amplitude, something like that, and you can see the window properties. So these are all the one important here when we have discussed about converting that into the PSD windowing and the buffer sizes. And you can see over here comfortably the 67% is normally used as a buffer size. Now, so I need to. So let us see about this data. So when you see here, so this is like a data from the engine, which we have an acceleration in a vertical axis. Let's say here. So now you can see here as a time domain signal, you can see the squiggly line from time of 0 to 50 hertz, 0 to 50 seconds, maybe a flat. And from 50 seconds to 630 or 640, you can see here something 620, it is like a squiggly line. Then there is a flat, something like that. It may not be much more activities which are happening. So if you try to convert that into a frequency domain, just pull this frequency spectrum and you can run this. Now you can see over here as a spectrum PSD, something like that. So from here, yeah, you cannot much to see. Say when we are talking about that, okay, what's happening here when I'm doing it over here? Say there is a time which is not happening anything, nothing is happening anything. Is there any chance that I can see something in the frequency domain? Is there any particular harmonics are visible in the particular time domain of somewhere around 630 to 670, something like that? Yes. So from this time domain, you cannot see anything over here. But when we try to convert that into a frequency domain, and from there, is there anything we can find it out? Let's look with that. Okay. So let me put it into this. Now what I do here, I will try to switch over here with that particular frequency, with that particular time frame of 630 to 676. Let me go to this place. I can choose this comfortably here by the way of selecting this. And once again, I'm doing this analysis here. Okay. Now you can see over here, there are certain kind of situation happening in the 40 hertz frequency. Okay. So from here also, as a comparison of this, as a selected portion of this data, is there anything is happening? So you see something like 40 hertz is some harmonics which may be present over here. So in a better way, if we are seeing that into a different picture, let's just do it here. So now what I do here, I just put the data here again back. So I would like to try to see here in a waterfall display as a joint frequency analysis. Now I can use this joint frequency analysis as a particular grid. So now we can see here. So there are certain different methodology possible. That's the reason. There is a short time Fourier transform as well as the Weber transform is possible. So I can see here in this joint frequency analysis. So already this has been made into that. So originally this was not like that. If you see here. Now I can see here as individual as 40 hits. So if you see here from 0 to 100 hertz, something like that. And if I do work here, I can adjust this. You can adjust this with the limits of, let's say, so I want this. This y-axis. I want to see that x-axis of 600. Removing this 636 and let's say and in the z-axis it is like okay. So you can see here by the way of closely seeing that 630 to 670, you can see clearly there are some harmonics which are present in this 30 hertz frequencies. Okay. So such a way this waterfall display as analysis will help you to arrive certain information about this the engine run-up frequencies which are present in that. Okay. So from the time domain, it is very tough to see here because from a time domain point of view, you know, see there are not much activities happening, but the engine is in ideal conditions. But there are certain harmonics present in the frequencies in waterfall or by the way of joint time frequency analysis. So this is demo 1. Let us see about that. Something like okay. Hey, how do we connect that waterfall and say we have what do you call the engine run up and combining this how the vibration changes with the engine speeds. So if we have the two signals like engine speed as well as the time domain signals like strain or acceleration signals, how do we connect these two to see here about that? Is there anything which are interesting to see here about the frequency or even for the particular? In addition to that, is there any order possible here? So this waterfall analysis can give you an idea about that in a particular signal, a particular frequency. Is there anything which is happening over here? Let me go to that. Just open that as a waterfall. So I have engine runner. I have two things here. Okay, let's say so I have a signal like RPM, which ranges from 1,300 390 to somewhere 3,100 RPM, and the accelerations, which is in the time is here. There are two channels of data, RPM as well as the acceleration data. Now I just put it into that to see about that how the order frequency and it's the order. Say here I have a revolutions. So this depends upon the revolutions, and it creates based on the tacho, and it creates that particular order and its frequencies. So I can show here as a slice display to show which order is my preferences in a slice display over here. Okay. So if I wanted to see some different kind of order, I can see over here. Say let me show it an order of let's say 0.5. So I can comfortably see here as a slice display. Okay. So now it moves into that order. So interactively, I can press this in a longer way. I can see here, if I keep on moving here, I can see that particular order. Okay? So which keeps on moving here. If I just click it here, so it can keep on creating that particular order into that. So interactively, I can work on this. So now you can see here. So whatever the order we have clicked here, it has been directly selected in the cursors. So let me have just order two. Okay? So this particular order analysis is very well quite possible here. About that. Okay. So which order is predominantly happening over here, right? So in a waterfall display. In addition to that, if you see here, so if you see the way we discussed about window and other functions. So by the way of amplitude, output is the amplitude, and the window type as a scanning window. So you have dozens of window possible, and the buffer size. Now, many times we have questions like which buffer would be quite suitable to use that, and what kind of a window is possible to use. Okay, so this is the normal question happens with the most of the customers and most of the test engineers. Okay, so a very specific answer to this is most of the time, majority of the time, and the handing window is used. In addition to that, there are certain kind of a engineering judgment, depending upon the signal what we have. Say whether the signal has a higher magnitude or somewhere it is like a peaks or something like what do you call it, the hot anywhere as a pothole signal, or there are some transient. So this kind of a judgment is purely from an engineering point of view. Now there is one more check is possible. Now I have used this 1024 as the buffer size. So by the way of seeing this particular buffer, you can see here as a points overlap, which happens in a positive way. Okay, so that means the buffer which are quite enough to create this kind of points overlap over here. Now, if I change that into the buffer size, let's say instead of 1024, okay, so please remember that if I keep on changing this buffer size into higher and higher size, it takes more time to do the computation depending upon the size of the signal. Say, let's say if I just change into from 1024 to, let's say, 256. So I may notice some of the differences, something like that, in the point of overlap. So you can very well notice here, there are certain negative values which are happening here. So the simple takeaway is, if this kind of a negative value which you feel that it may not be a comfortable size of the buffer. Now try to change it with that again, the 512, because you may lose some of the signals and its analysis. Now we can see here over there are certain positive values which are happening, only the positive values. Okay. So this kind of a quick possibilities to see which buffer and the window is quite reasonable for the given time sequence. Right. So from a waterfall analysis, we could able to see the individual frequency content and its individual display, as well as the slice of that particular order, okay, in a way of seeing that into as a joint spectrum, okay, time as well. So this is like a three-dimensional spectrum we can see over here. When you are clicking over here, it becomes like a three-dimensional picture. Okay? You can see here as a frequency, speed, and the amplitude, because the speed is the one which we have it in a time domain, okay, as amplitude in the G. Right. What else we have? Okay, waterfall analysis. Right. So the next joint time frequency analysis is the frequency response function or the transfer function, which are basically calculating between the two signals of structural behavior. Say when you have structures like a big in nature, big in this. Okay. So you can see here there are two signals which are captured here as as a what do you call the excitation as well as the response. So you can compare these two to monitor how the structures behave. In another way, it can be easily possible to see as a shaker testing to see the modal parameters. Okay, so as an excitation and as a response. So you can see here as a gain as well as the phase and things like that. Right. So as a frequency response, which helps you to find out the gain as well as the phase. Okay. So from a structural point of view, you can see here comparing with the two signals where there is a different kind of scenarios happening. Now you can see there may be a possibilities of fatigue damage or something like a damage which may be happening as a crack, which may be initiated over here, comparing to one over the other place, the location of the sensors. So this kind of scenario is possible in the frequency response analysis. Let me show you one quick on this frequency response analysis. Say what I just. So this is like a shaker test on a component. As a force is applied over here, and the response is getting as a response, excitation and the response. So from here, what I can see here is the comparison of these two. Okay, as a gain as well as the phase. So it could be able to see here. And in a waterfall, this helps me to see how this pattern look like. Say here the gain which has seen in the waterfall display have a similar pattern, and of course with the similar what do you call the same you can see here over here with the same amplitude, something like that. So this frequency response function helps you to check as the linearity by the way of applying this waterfall display. What we have done here is we have clubbed together with the time as well as the frequency domain analysis by the way of joint time frequency analysis. So this helps me to identify how the frequencies are changes over the time with the signal. From a waterfall display, we have learned that how the frequency changes with respect to another parameter, something like engine speed or the tacho. So in this case, it's RPM. As a frequency response analysis, which helps me to identify the relationship of frequency between two signals. So either it is excitation and response, something like that, or it can be of a big structure we monitor over with a different data points and different locations of the sensor data points. Such a way, this linking time domain as well as the frequency domain helps me to put more and more insight into the signal to arrive many more informations to take a decision on that.